5.7, Inverses and Radical Functions. Now we discussed inverse functions back in section 3.7, but here's the definition just as a refresher. And if you want to see an in-depth discussion of this definition and some inverse functions, go back to that section. Two functions f and g are inverses of one another if for all x in the domain of x and g, g of f of x equals f of g of x equals x. So if they undo each other and we come back to the identity function, then that shows they're inverses. So example 1 says show that f of x equals 1 over x plus 1 and f inverse of x equal to 1 over x minus 1 are inverses. To show that they're inverses, we want to consider f of f inverse of x. And it's sort of presumptuous to say that one is f and one's f inverse, since we are about to show that they are inverses. Alright, so that'll be f of 1 over x minus 1. So our inputs into the function f will be 1 over x minus 1. So it's 1 over input plus 1. Inputting that, 1 over x minus 1. Simplifying this, we get 1 over x because we have minus 1 and plus 1. And then that is x. So these two are inverses because composed with each other, we get the identity function. Now example 2 says find the inverse of this function. F of x equals 5x cubed plus 1. The general strategy here is to rewrite this as y equals 5x cubed plus 1 and solve for the input, because we want, in the end, our input to be the output. So we want this function as in terms of y, and we want our output to be inputs. We're switching the two. So we're going to solve for x, so subtracting 1 from both sides. Y minus 1 equals 5x cubed. Right, dividing by 5. That equals x cubed, and then the cube root. All right. Now, this is actually one of our toolkit functions, the cubic function. And we discussed in 3.7 that function is in fact one-to-one, so defining an inverse this way makes perfect sense. Let's make that a little bit more obvious. That's the cube root equals x. So we can perhaps write f of x, or f inverse of x equals the cube root of y minus 1 over 5, or we can write that in terms of y. We could either say, let's put both of these down, f inverse of y equals the cube root of y minus 1 over 5, or f inverse of x equals the cube root of x minus 1 over 5. Just a change of variable so that we can plot them on the same coordinate axes if we would like. Now, if a function is not one-to-one, so in this case the cubic function and the cube root are both one-to-one, but if they're not, if the function we're dealing with isn't, then we need to restrict the domain so that it becomes one-to-one, making a new function, and then that new function will have an inverse. So in this example we have find the inverse of f. F of x equals x minus 4 squared, with the restricted domain of x being greater than or equal to 4, and f of x equals x minus 4 squared with a domain restriction that it's less than or equal to 4. Both of these are going to actually have the same process, okay, but we will have two different functions based on our square root. So let's go ahead and write this as y equals x minus 4 squared. And taking the square root, I get square root of y equals x minus 4. Then I'll add 1 to both sides, or add 4 to both sides, so x equals 4 plus the square root of y. Right, so that f inverse of x, I'll go ahead and write it in terms of x, is 4 plus the square root of x. Alright, now for the second function, or this restricted domain, but a different restriction, what's going to change, okay, so well, let's just go ahead and say the domain here was x is greater than or equal to 4. The range, when you say it's greater than or equal to 4, okay, is y is greater than or equal to 0. If x is less than or equal to 4, then my range is it's also y is greater than or equal to 0, which is where the problem lies. So switching these two, we need to have something slightly different. So for this function, it's going to be f inverse of x equals 4 minus root x, because of the way our domain is restricted. Okay, we have a plus or minus square root, remember that. Alright, next we want to restrict the domain and then find the inverse of f of x equals x minus 2 squared minus 3. Okay, same process. So restricting our domain, well, this function has a domain of all real numbers and a range, well, let's see, hk, so it shifted down, so y is greater than, just go ahead and write it this way, it's opening up, so y is greater than negative 3. So when I find the inverse, my domain is going to be greater than or equal to negative 3. Negative 3 to infinity. All right, so let's go ahead and take that fact, and then we'll want to take y equals x minus 2 squared minus 3. Adding 3 to both sides, y plus 3 equals x minus 2 squared. Taking the square root, that is the square root of y plus 3 equals x minus 2, making, I'll go ahead and switch this around. Now wait a second. Adding 2 to both sides, this is 2 plus square root of y plus 3. Now, because our domain is going to be, for our inverse at least, because our domain is going to be greater than negative 3, okay, this works just fine. Okay, this function is defined. So f inverse of x equals 2 plus square root of y plus 3. All right. See, so our range is going to be, our range should actually be negative infinity to infinity. So we have that's why it's 1 to 1. When I restrict it, my range or my domain actually goes from 2 to infinity. And so now my range is from 2 to positive infinity. So that does in fact work. All right. Same idea for this next problem. Restrict the domain of this function and then find the inverse. All right, well, our domain, let's go ahead and write our domain and our range. Our range is greater than or equal to 0, and that is for values beginning at 4 and going to infinity. So we'll restrict our domain to x being greater than or equal to 4. So when we switch these for our inverse, the domain and range, we should end up with a domain of 0 to infinity and a range of 4 to infinity. All right, so we'll write this as y equals root x minus 4, squaring both sides. We have y squared equals x minus 4, and then adding 4 to both sides, y squared plus 4 equals x, so that f inverse of x is x squared plus 4. And the range of that function is greater than or equal to 4, and the domain will be x is greater than or equal to 0. In fact, let's go back to number 4 and mark that. This is true if my inputs, okay, if my domain is x is greater than or equal to 2. Example 6, a mound of gravel is in the shape of a cone with a height equal to twice the radius. Radius. The volume of the cone in terms of the radius is given by v equals 2/3 pi r cubed. Find the inverse of the function that determines the volume and is a function of r. Then use the inverse function to calculate the radius of such amount of gravel measuring 100 cubic feet. And we're going to, let's not use pi equals 3.14, let's use an actual value from a calculator. Alright, so v equals 2/3 pi r cubed. This function is a cubic function in terms of r, so it is 1-to-1 and we can find the inverse. So let's first isolate r, so we'll multiply by 3/2. In fact, let's multiply by pi over 3 over 2 pi. Alright, and that will equal r cubed. Alright, and then we can take the cube root of both sides, so that the radius can be found by the equation cube root of 3 over 2 pi times v. There's our inverse function. Now, if we have a volume of 100 cubic feet, then the radius, we'll evaluate this, so radius equals cube root of 3 over 2 pi times 100 . 3 over 2 pi times 100, closing my parentheses, that is 3 point, or it's approximately 3.628. We'll go with that. So the radius, 3.628 feet, because the radius is in feet. All right, for our next problem, we want to find the domain of a function. A fairly complicated function, so we have a couple of things we need to look out for. One is that we cannot divide by 0. Okay, but in this case, we're really dealing with a radical function. We need to make sure that our input to the radical function, that is greater than or equal to 0. All right, so x plus 2 times x minus 3 over x minus 1 must be greater than or equal to 0. Okay, so, and we also cannot have x minus 1 equal to 0. So we already can say that x is not equal to 1. All right, so what is going on here? The places where it's going to be equal to 0, okay, actually this is the way I'm going to do this. We know that strange things happen at 1, -2, and 3. 1, it is undefined. At 3, the function is 0, and at -2, the function is also 0. So I want to test some values. Let's pick x values in here, in each of these intervals, and see which ones of those are, in fact, greater than or equal to 0. So I want to use an x value of -3. Let's see, no, let's go with 0. 0 is a very good choice here. We have x equals 2 and x equals 4. So let's evaluate this function at each of those values. Let's see, x plus 2, x minus 3 over x minus 1. Okay, so let's go ahead and do that for -3. At -3, it is a negative value of the function. At 0, value is positive. At 2, it is negative, so in between those two. And at 4, it is positive. So we have several intervals where it's greater than or equal to 0. Okay, greater than or equal to 0 is between -2 to 1, not including 1 because it's undefined there, as well as from 3 and on to infinity. So sketching this graph is actually a good idea of what's going on here, because it's a rational function. Okay. So we have our answer. Okay, here's our domain. I want to verify that with this. Okay, so the x-intercepts of this are, as we said, -2 and 3. All right, we have a vertical asymptote at 1. Okay, and because it's a linear factor, being a linear factor here means it's going to act like the reciprocal function. So let's find our y-intercept. If we evaluate this at 0, that is 2. So that's -1. All right, so that's 6. Okay, so at 0, in fact, we have our square root there. So the square root of 6. 0, square root of 6. We have our y-intercept. It has some linear behavior, okay, at 1. So we are going to have a function that goes through here, and it's going to approach infinity at 1. And it's going to have to decrease there because we don't have any bouncing. It has a linear action there at x plus 2. There's no squared term, so it's going to cross. It's also going to cross at -3, or at +3. Now, based on the fact that this is going to look like a reciprocal function, we're going to have something that looks like this. And the places where this function is greater than or equal to 0 is starting at -2 and going to 1, not including 1, and starting at 3 and going off towards infinity. So that domain does make sense with connection to the graph that we have. Our last question is the function c equals 20 plus 0.4n divided by 100 plus n represents the concentration C of an acid solution after n milliliters of 40% solution has been added to 100 milliliters of a 20% solution. First, find the inverse of the function. That is, find an expression for n in terms of C, and then use the result to determine how much of the 40% solution should be added so that the final mixture is a 35% solution. All right, so let's go ahead and write this again. 20 plus 0.4n divided by 100 plus n. Now we're going to multiply by 100 plus n on both sides. Multiply by 100 plus n. And I'm going to go ahead and distribute that. So that will be 100c plus nc equals 20 plus 0.4n. Now we want to solve this for n. So we need to get all of our terms with n on the same side. So I'm going to subtract NC is what I want to do. Actually, no, let's go the other way. I'll make it on the right side. So subtract 100C and subtract 0.4N. All right, so that means we're going to have a minus 0.4N and minus 100C on this side. Let's move those. So we're switching sides with those. All right, this should result with our terms with n on one side and the terms without on the other. So NC minus 0.4n equals 20 minus 100c. All right, now we can factor an n out here. C minus 0.4 equals 20 minus 100c. And we can then divide by c minus 0.4. Which means n equals 20 minus 100c over c minus 0.4. Now we take what was given to us. Okay, that's our inverse. Use the result to find the amount of 40% solution that should be added so that the final mixture is 35%. That means we're actually trying to find n when c is equal to 0.35. So let's evaluate this at 0.35 minus 100 times 0.35 divided by 0.35 minus 0.4. All right, our numerator is negative 15. Our denominator is negative 0.05, which means we should have 300. There was no decimal in the numerator. All right, so n equals 300. That means to have a 35% solution, we need to add 300 milliliters of our 40% solution. All right, that is the end of this section. So, a couple of big topics to look for, okay, is obviously finding domain can be tricky. Okay, and finding inverses. So if you need to, please review back in Chapter 3, Section 7. There are lots of examples there of inverse functions and finding them, especially the restricting domains.